Okay, welcome to the Climate Impact of Machine Learning session. I'm Nicola Fusi. I'm a researcher at Microsoft Research New England in Cambridge, Massachusetts. Um, and the reason I think many of us are here is that we are kind of seeing that the cost of training machine learning models is increasingly becoming a problem. And you may have seen this article in The Economist that discusses this issue, and you may have seen in that article kind of this picture that is making the rounds is based on data from OpenAI. But The Economist did a pretty good job at kind of disentangling the various tasks that people have been trying to tackle over the years and the energy consumption. So you see time on the x-axis, computing power used on the y-axis, and you see that roughly AI can be split in 2 years from this point of view. The first era goes up to 2012-ish, and it's where the power consumption doubles every 2 years, kind of following Moore's law. And then in the modern era, you see a doubling that has increased in speed, then it doubles over 3.4 months. Uh, and you can see that this holds across different tasks, vision models, computer vision models, speech, language, games with reinforcement learning agents. And it's becoming a serious problem because as you keep going in time, you can see that the power consumption is becoming untenable. And this is part of the reason why personally I'm here. My research interest is in automated machine learning, Bayesian optimization, and automated model design. And this is what the typical table I see in our papers. It's a typical table I put in my own papers, and I protected the innocent by blurring most of the table out. But you see that um, you have a certain search cost. Basically, the idea with AutoML is that you replace human time with computation. But the question is, what's the multiplier on computation? Uh, and you basically see that there are approaches that take 3,000 GPU days to search over models. But on the other hand, you see that the test accuracy on a benchmark test, this is ImageNet, is kind of all in the same ballpark. And over time, these are roughly in chronological order. You see that over time, things become cheaper and cheaper. But still, I would argue that even a couple of GPU days is a significant amount of time. So when I started seeing these tables in papers in my own domain, I started getting worried because AutoML is a thing that you do on top of already expensive models. So as AutoML becomes more expensive and as models get more expensive, things become really out of control a little bit. Um, so that's kind of my means of introduction, but I'm really grateful to all the three speakers. They are incredible researchers in this area, and I'm really, really grateful that they agreed to present. Um, the first speaker is Emma Struble from Carnegie Mellon University. The second speaker is Vivian Zi from MIT. And finally, we have Diana Markolesk from UT Austin. And they're going to each present, have a talk, and then at the end, we're going to have a panel joint across all of us. And finally, I want to acknowledge my co-organizers who have done most of the work for this in practice. In particular, Phil Rosenfield, who was a senior research program manager at MSR New England in Cambridge as well, and Sharon Gillett, who was a technical advisor and senior principal research program manager in our lab as well. And with that, let's hear the speakers.
Hi, I'm Emma Strubel, and thanks for having me. I'm doing a one-year postdoc at FAIR before starting at CMU as an assistant professor in the fall. And my goal this year at FAIR has been to figure out how to actually be able to train and use pre-trained language models like BERT once I'm at CMU in the fall, and of course have far fewer compute resources. So today I'm going to talk a bit about why that's important to me, even as an academic, survey some recent approaches for making these models more efficient. And then if we have some time at the end, I'll identify some promising future directions. So as you've probably already noticed, recent advances in techniques and improvements in hardware for training deep neural networks have enabled really impressive accuracy improvements across many fundamental tasks of machine learning. So in NLP, we've been naming these models after Muppets and more recently other cartoon characters, with the largest and most computationally hungry models tending to obtain the highest scores. So here I've plotted on a log scale the number of GPU hours required to train 4 recent NLP approaches. This transformer, which is a machine translation model, Elmo and BERT, which are pre-trained language models that are used for a ton of different downstream NLP tasks, and the evolved transformer, which is neural architecture search applied to the transformer. And so as you can see from this plot, the number of GPU hours required to train these models has increased seemingly super exponentially over the past about 3 years. And since I originally wrote the paper where we quantified some of the energy requirements of these models, this trend has continued. So Google's Mina chatbot, which was announced in January, was trained using neural architecture search on 2,048 TPU cores for an entire month. And of course, GPT-3 was announced just about a month ago now. And while it's hard to place it exactly on this chart, it's estimated that it required about 12 million US dollars worth of cloud compute resources to train a single model. And as a point of comparison, training the evolved transformer required only about $150,000 in cloud resources. So the point I want to make here is that the energy consumption of these models is growing in step with their computational requirements. So here I've listed the carbon footprint in pounds of a number of common, or what used to be common benchmarks, such as air travel for one passenger between New York City and San Francisco, and the carbon emissions for the average American for 1 year. So in a paper that I presented at ACL last year, we quantified the energy required to train and develop deep neural network models for NLP, and we converted that to estimated cost in terms of cloud compute credits and carbon footprint. And so we found, for example, that the GPU time required for me to tune and develop a model that I presented at an NLP conference a couple of years ago, like effectively doubled my carbon emissions that I would have otherwise produced that year. And training a machine translation model using neural architecture search, if done using GPUs, could produce more than 2 times as much carbon as a car during its lifetime, including fuel. And as I pointed out in an earlier slide, we also estimated that this model would cost about $150,000 in TPUs to train, which highlights another important side effect of the enormous computational requirements of these models, which is that they're becoming increasingly limited to a really small set of researchers and practitioners who actually have access to these enormous resources that are required to develop and deploy these models. So most of the carbon footprints that we computed for that paper, and that I'm citing in this plot, are for training really large models, like large pre-trained language models like BERT. And you may be thinking, well, let's leave the training of those models to big companies and whoever else maybe really cares about supervised English leaderboard chasing. But I actually think it would be hugely beneficial for researchers and practitioners outside of a few privileged institutions to be able to work with these models. So for me, for example, I'm mainly interested in solving problems where solutions can be found in text, like many of you maybe are. So for example, here I'm showing a caricature of a project I worked on with material scientists at MIT, where our goal was to automatically extract inorganic materials recipes from the text of journal articles. So of course, the reality of getting this recipe out requires inducing some kind of structured annotations over the unstructured text. So in our case, this is some form of syntax and semantics, which could also be thought of as entries in a knowledge base. So this is an example of a problem that I think is interesting. And some of the best approaches for obtaining the structured information that we want from the raw text require good distributed representations of words. And large language model pre-training just does a really great job of building these representations of words in context. And in a way where you can get pretty substantial improvements, not only in supervised learning, but also in the unsupervised setting or in out-of-domain performance, where the data that you test on comes from a different distribution than the data that you trained on. All of this is sort of, as long as you have a large corpus of unlabeled text in the domain that you care about, which is often the case. So my point here is that even though I'm not necessarily trying to beat Google or Microsoft on a question answering leaderboard, as someone who's interested in making NLP tools that are useful for extracting structured information from unstructured text across a wide variety of domains, like such as the collaborators that I mentioned in materials science, it would still be really useful for me and my collaborators to be able to train and use the representations that come out of these big pre-trained language models. Right, so I started by pointing out that although these models can provide high quality representations of words in context, which can be useful to researchers such as myself, that comes at a huge computational cost, which makes it inaccessible to most researchers and practitioners. So Now I want to talk about some techniques for scaling down these models, ideally with minimal impact on the quality of the representations that they produce. But first, I'm going to briefly remind you how they work to make sure that we're all on the same page before describing how they might be made more efficient. So essentially, all mass language models are based on the transformer architecture, which consists of J stacked neural network layers, with the output of each layer provided as input to the next. So this allows the model to build up increasingly complex representations of the text with each additional layer. And as a quick reminder, this is what the internal mechanism actually looks like inside of each of those layers. So this is a figure from the original paper from 2017. It consists of multi-head self-attention, which has runtime that's quadratic in the length of the input, followed by a large feed-forward projection, which is linear in the length of the input. And then after the final layer, there's a softmax layer, which predicts into the entire vocabulary of tokens. Okay, so this neural network architecture is the basis for a lot of state-of-the-art NLP right now, including BERT-style mass language models. And while there's been other architectures that have come out, like GPT and XLNet, and they do differ slightly, the overall structure is similar enough that I think many of the same ideas apply. All right, so the way that mass language modeling works is that rather than providing all of the tokens to the model, each time a sentence is observed during training, some of its tokens are masked. And the objective that the model is trained to perform is to predict what the masked tokens were. So in practice, it's been found that it's best to mask about 15% of the tokens. So in this fragment, that would be one token. We don't actually train on sentences. We train on long sequences of sentences of about 128 to 512 tokens in length. And tokens are actually, not tokens or words, or they're not words, but they're subword units, byte pair encoded subword units. So typically limited to a vocabulary of about 30,000 word pieces. And this alternative training objective compared to traditional language modeling, where each token is predicted incrementally in like reading order from the past context. This allows for much faster training, since predicting the masked words can be parallelized on GPUs and TPUs. And this is really, or at least in part, what's facilitated training these huge models on enormous quantities of data, which has led to way better performance than older LSTM-based language models. Okay. So how can we improve the efficiency of training these models? So Roy Swartz and Jesse Dodge and others at AI2 characterize this in a simple equation that I really like in their Green AI paper. So they define the cost of obtaining a result as proportional to the cost of processing a single example with the given model, multiplied by the size of the data set, the number of examples you're training on, multiplied by the number of hyperparameter configurations required to fit a good model. So I'm going to start by describing some recent techniques for reducing the computation required to process a single example, which is by far the most popular approach to trying to improve efficiency in these models. Right, so the premise behind a lot of these techniques is that these large models are actually really over-parameterized, but training a smaller model from scratch just doesn't perform as well as training a larger model first and then making it smaller post hoc. So we think this is an optimization issue, and there's an interesting recent line of work based on the lottery ticket hypothesis, which basically suggests that large models work better because their random parameter initializations are more likely to contain lucky values that converge to good performance. But so one popular approach to making models smaller is known as knowledge distillation. So the idea here is to take a large model that works well and distill it into a smaller model by training the smaller model to imitate the larger model's predictions and intermediate activations. So this picture here is from this paper by Sen et al. And it's showing two of these transformer self-attention layers, and the dotted lines between sort of like the two layers are indicating the places where the larger model is trained to imitate the smaller model. And this works reasonably well. There still aren't any approaches that I know of for distilling BERT that work as well as the original model. And of course, this also requires that you have a pre-trained model that works well for your task sitting around already, and you just want to make it smaller. Oops. So another popular approach is taking a pre-trained model and removing or pruning unnecessary model parameters. So There are a lot of different examples of this. So for example, you can prune different parts of the model, or you can propose different metrics for what makes a parameter prunable. So a common example is just to prune the smallest weights. And so this figure is from a recent paper by Paul Michel at CMU on pruning self-attention heads from transformers. And this histogram is basically showing the number of heads that can be pruned for the model while maintaining a given accuracy on machine translation or in language modeling or fine-tuning on MNLA. And you can see that not only are many of the heads prunable, but in some cases, pruning heads actually improves accuracy, presumably by sort of acting as a regularizer. So another approach that I really like that's similar to pruning is quantization. So now instead of removing parameters, entire parameters, the goal is to decrease their precision or the number of different values that they can take on. So typically models are trained using 16 or 32-bit floating point numbers, but this can actually be reduced to as low as 2 to 4 bits per parameter. And so this can vastly reduce memory requirements. And depending on the underlying hardware can be extremely fast. But it does require that the underlying hardware actually has the specialized instructions to support math in on these lower precision values. But as with training models with fewer parameters, training models with less expressive parameters is a lot more challenging than taking a pre-trained model and quantizing it post hoc. So again, you generally need to start with a big model and then make it smaller. Okay, so the last category of approaches I'm going to refer to as bespoke architectures. So these are model-specific modifications, usually to reduce like the quadratic all pairs self-attention that is the computation bottleneck in the transformer. So just as a brief aside, going back to a little illustration of the transformer, so in my personal experience profiling an equivalent to a BERT language model, about half of inference time was spent in the multi-head self-attention, about a quarter was spent in the feed-forward network, and about a quarter was spent in the softbacks. So the bulk of the computation is happening in the self-attention, so most approaches focus on reducing computation there. It also makes intuitive sense that we should be able to do this, because every token really should not have to attend to every other token, especially since the model is like iteratively aggregating information from the context into each token's representation at each layer. So one of these example architectures is using known as the reformers, using hashing to cluster token representations, and then it only computes self-attention between tokens that are in the same cluster. So these are tokens that already have like the closest representations that are going to have the highest dot products. Other set of approaches is factorized attention or sparse attention, where the model attends to a subset of its neighbors according to a fixed width pattern, like every other token or every 3 tokens in the sentence. And another example is training the model to attend to fewer tokens by learning for a given token to attend to a smaller or larger window of context. So like certain tokens may need to look at more tokens versus less tokens. So one of the nice things about this set of approaches is that unlike the other methods, they can be used to train the model more quickly from scratch. But of course, there's always a trade-off between efficiency and accuracy. And one thing that remains largely untested in many of these approaches is how well they generalize to new data or how efficiently they can be fine-tuned. But that's the topic for a different talk. So that was a sampling of the many approaches that have recently emerged for improving per example efficiency. And I'm not really going to go into detail about approaches for improving the number of hyperparameter configurations, except to say that model sensitivity to hyperparameters is woefully underreported in papers. And I think we need to do a lot better to clearly characterize when models are more or less sensitive to hyperparameters and are therefore going to require more computation to do fine-tuning to actually deploy on new data. But what I've been interested in looking at recently is reducing the amount of data that these models are trained on, because I think there's actually a lot of potential leeway there, and potentially some interesting things to learn as well from better understanding of which examples are more informative versus less informative for training these models. So reducing the size of the training data is starkly in contrast with the recent trend. So in this tweet, Colin Raffel, who's a language model researcher, worked on T5, says, hot take, the most surprising thing about BERT isn't how well it worked when it was proposed, but how much better it would have worked if they had just pre-trained for longer on a more diverse data set. So indeed, since BERT was first released, big companies have clamored to scale up training in terms of both model size and the amount of training data, which these two things go hand in hand. So Microsoft isn't on this slide, but they're also participating in this with their Turing NLG model. Um, but what I want to show here is that, to me at least, it seems like naively adding more data is not an efficient way to improve performance. So we see similar trends in Roberta and XLNet, which are two post-BERT language models from Facebook and Google, respectively, where about 10 times more training data, the same model can obtain about a point or two absolute in terms of F1 or accuracy, across various common language modeling benchmarks, which is equivalent to about a 10 or 20% error reduction. So, but my intuition is that we really don't need all 126 gigabytes of training data or 30 billion tokens to learn the same models. So as an alternative to making models smaller, I think it would be really beneficial if we could figure out how to better select an informative subset of examples from these enormous corpora for training the model. So what's been done towards this end of improving sample efficiency? So the closest thing I know of is the Electra model from Kevin Clark and collaborators at Stanford and Google. So as an alternative to the mass language modeling objective that I described before, Electra makes training more sample efficient by setting up training such that the model gets a signal from every token in every example rather than only 15% of the tokens in each example. And they do this by dividing the model into a generator and a discriminator. So the generator is basically just a small mass language model, and its predictions are provided as input to the discriminator, whose objective is to do a binary classification on each token, identifying whether each token was from the original sentence or generated by the generator. So it performs best when the two models are trained together at the same time, which I think is really interesting because the generator is essentially inducing a natural curriculum for the discriminator to learn from, since presumably earlier during training, the generator's predictions are worse than later during training. And this raises an interesting idea. Should we be doing curriculum learning or active learning for language model pre-training? So I've been taking a look at this, and so far I haven't gotten anything super straightforward to work. And one key question that arises is what makes it easy versus a difficult example for a large language model? I think we don't know the answer to that. So to get a sense for this, I applied a simple study initially proposed in computer vision to better understand which examples are more or less difficult for mass language models. Specifically, I applied this to the Roberta language model. So the analysis is pretty simple. So during training, you just maintain counts of how often the model changes its prediction for each token in the corpus. The intuition being that tokens with a high forgetting count are the most difficult because the model kind of like isn't doing a good job of learning, what its prediction should be for those tokens. So this is an example of what those counts look like on like an actual sentence. So I've colored the tokens here according to forgettability, with red and orange being the most forgettable or difficult, and blue being the least forgettable and easiest. So you can see here that the easiest words are mainly determiners and the verb to be, and the hardest words are pretty clearly these content words like modifiers and nouns, like the word metaphors or different. If we zoom out and look at corpus level statistics for what are the least and most forgettable tokens, this trend continues. So the most forgettable or hardest words, once you filter for words that occurred more than 100 times in the training data, and this is Wikipedia training data, these are really specific verbs and nouns. And the least forgettable or easiest are punctuation determiners, and of course super deterministic subword pieces like ricane, like only happens after her in English. And so this makes a lot of intuitive sense. So the most forgettable words are exactly the words you would expect to have sort of like the highest entropy distribution in the softmax for a model trained to do language modeling. Because who's to say whether the next word is shimmer or sparkle, and which one is correct given the context. Yeah, so if we plot this token mean forgetting count averaged over the corpus versus token frequency as a 2D histogram, we also see that it's not necessarily the infrequent tokens that are forgettable, but the medium frequency tokens, like all these medium frequency content words. So I guess my takeaway here is that determining example difficulty in a way that is really going to impact training is a bit harder than looking at sort of like really maybe the most obvious metrics like token or bigram frequency, or even output distribution entropy, because just focusing on the helplessly ambiguous examples, isn't going to accelerate training either. So we need to figure out some middle ground way of finding examples that'll help the model learn to disambiguate predictions that are actually disambiguatable. I think we don't know yet what those examples exactly look like. All right, so now I've summarized a bunch of work that's out there and given you a little taste of the stuff I've been thinking about lately. So now I'm about done, and I think I'm actually out of time. So I'm not going to summarize a few future directions, but I will leave you with this slide to look at and maybe discuss in questions. Yeah, Yeah, and thank you so much for listening. Yeah, I'm excited to take your questions live.
All right, so it's great to be here today. I'm excited to talk to you about the role of efficient computing and reducing the carbon emissions of machine learning computing and discuss some of the challenges and opportunities that we have in this space. So it should be no surprise that there's been a growing demand for computing, both in the data centers as well as in our devices. And a lot of the factors that drive this computing comes from the demand for machine learning and also the amount of compute required from machine learning. And so it's been growing exponentially over the past few years. So this is something that we really need to address, in particular because the cost of computing connects to carbon emissions. So let's see how this connection resides. So we start with what do we actually want to compute? This requires knowledge about, what are the compute demands? What is the task that we're computing for? What are the requirements for that? And typically, in order to achieve that task, we might have some form of computing algorithm that we need to run. These days, typically a DNN or deep neural network model. Then that algorithm becomes a workload on some form of computing hardware itself that does the computation and turns out the results. And together, we can say that this is how we actually compute. So the computing algorithm plus the computing hardware. Now, to drive the computing hardware, we have some form of compute energy. And where does this come from? Well, it often is dictated by two aspects: the energy source, which basically converts, energy and also generates some carbon emissions. And then when it generates the energy, we need to deliver this energy to the computing system itself or make it into compute energy. So there's some energy delivery there. And there's also some factors called, like, for instance, like cooling. Since the computing hardware generates heat, we need to cool it in order for it to operate. Now, these two factors of energy source, energy delivery, and cooling really depends on where we're going to actually compute. So we'll cover these three topics in today's talk. We'll first focus on how to compute, then we'll discuss where to compute and what we're actually computing, and look at various opportunities and challenges in these spaces. So let's start with how to compute, in particular, the computing hardware itself. So one of the big challenges in designing, efficient computing hardware is that transistors are not becoming more efficient. So over the past few decades, we had Moore's law, which was giving us faster and smaller transistors, and we had Dennard scaling giving us more efficient transistors. But we can see that this trend has really leveled off over the past decade. And so we really need a new approach to, make more efficient hardware. And one of the approaches is to design specialized or domain-specific hardware, rather than using general purpose CPUs, in order to achieve significant improvements in both speed and energy efficiency. So if we're going to design specialized hardware, we need to first ask the question, well, where is the energy going in the hardware itself? And so as it turns out, energy is dominated by data movement. And what I mean by data movement is that, basically, how do you deliver the inputs to your computing engine? Let's say you need to do a multiply. How do you deliver the cost of delivering the inputs to the multiply itself, and also the cost of, writing out the results of that multiplication? Now, if we compare the cost of doing these arithmetic operations like multiply and adds to memory reads or data movements, we can see that there's a drastic difference in terms of energy consumption. So for example, reading from a very small on-chip memory, like an 8 kilobyte memory of SRAM on the actual system, reading 32 bits of that, it's already going to cost more energy than a 32-bit floating point multiplication. And this energy is going to increase even more if we look at the last line when we read the data from off-chip memory. So the further the data needs to come from, for example, from DRAM, the more energy costly it's going to be. And I should highlight that the scale here is in the exponential scale. In summary, memory access is going to be orders of magnitude higher energy than the cost of computing these arithmetic operations. And that should be what we really want to focus on if we want to build energy efficient hardware. Now, if we start thinking about how we can reduce the amount of memory access that we have, or the data movement cost, one thing we can do is exploit data reuse. In particular, there's a lot of data reuse opportunities in deep neural nets, and this basically means if I access a piece of data from memory, can I reuse it multiple times for different operations? And there's a lot of opportunities for this in DNN. So for example, if we think about convolutional neural nets, we have what we call convolutional reuse, where the activations and weights, the same ones, are going to be used just in different combinations for different multiply and accumulate operations. We also have feature map reuse, where we apply multiple filters to the same input feature map. And so as a result, any activation in the feature map is going to be reused multiple times across the different filters, or you can think about it as generating across the different output channels. And then finally, you'll also, if you're going to process more than one image, so if your batch size is greater than one, we're going to have filter reuse because each weight in a given filter is going to be reused multiple times across the different feature maps. So we want to be able to exploit this reuse. We also want to have the right hardware that allows us to exploit this reuse. And this reuse can be exploited with hardware that contains low-cost memories. And by low-cost memories, what I mean is very small memories, under 1 kilobyte. And the benefit of these small memories is that it's very cheap. It's located very close to the compute. And so accessing these memories is going to be very low energy. So just to give you an idea, let's say a multiply and accumulate in an ALU costs 1x. Reading from a very small memory, which is under 1 kilobyte, is also going to be the same amount of energy. As compared to if you read it from a larger memory, like a global buffer, which is about from 100 to 500 kbytes, it's going to be 6x the energy. And of course, going to DRAM is going to be way worse. And so in general, the farther and the larger the memories, the more energy and power it's going to consume. So the key idea is ideally, I want to reuse and read my data from these very low cost memory. So I read it once from this very expensive memory and then reuse it multiple times in this very small memory. The challenge, of course, is these small memories are small in capacity, and we have these very large neural net with millions or billions of parameters and activations. And so what we need to do is we need to chop up this very large neural net into smaller chunks. And then we need to figure out, what is the order of chunks that we should process in so we can maximize the data reuse. And these chunks have to, of course, fit in this low cost memory. And so the order of, processing these different chunks is referred to as the data flow. So how the data flows through the system and how can we exploit the most reuse. And there's been a lot of research in this space. One approach is a data flow that we explored in the Iris architecture. And this data flow really tries to balance the amount of reuse across the various different data types, weights, activations, and partial sums. And by having an efficient data flow, we can exploit enough reuse to reduce the amount of memory access from this global buffer by 100x and reduce the amount of off-chip memory access, which is the most expensive, by over 1000x. And so actually we realized this Iris architecture in an actual chip that we fabricated. And when we measured the power consumption of this chip, or the energy consumption of this chip, it's an order of magnitude more energy efficient than a mobile CPU. Really, again, by focusing on minimizing data movement through energy efficient data flows that exploit reuse. Now, this is one approach for doing this. If you look at more emerging architectures in terms of how to reduce or make computing hardware more efficient, one area to explore is in-memory computing. And the idea here is if we want to reduce data movement, why don't we just move the compute into the memory itself as opposed to sprinkling some memory beside the compute? And the idea here is, can we perform computations with the memory storage elements themselves? In order to do this, we actually have to turn to analog computing, which basically means we need to represent the activation weights and the partial sums using analog voltages, currents, and resistance. So for example, one way to do this is that your activations are represented by voltages, your weights are represented by the conductance of a resistor, which is the storage element itself. Using Ohm's law, when you multiply the two, you get a certain amount of current that comes up, and that's already going to be the product. And then finally, using Kirchhoff's law, you're going to accumulate the current across these different resistors, and then that's going to do your accumulation itself. So as a result, you get a free basically multiply and accumulate by computing in the analog domain. Now, there's some challenges here as well. Of course, there's going to be increased sensitivities to the non-idealities of these devices, of the resistors and so on. And then also, since you're doing the compute in the analog domain, there's going to be overhead to compute to basically convert from digital domain to analog domain and back. There's a lot of exciting research into this space. In particular, there's a lot of work on coming up with new memory devices that are more efficient for this computing and might be suffer from less non-idealities. Another way to do efficient computing is actually using light rather than electricity. So the cost of moving a photon can actually be independent of distance. So as we mentioned before, often, in terms of for electrons, if you move it further, you're going to consume more power. But here, it's going to be independent of distance. And also the multiplications can be performed passively in light as well. So that also makes it more efficient. You can think of, these are two examples of some processors that are designed with light. And some of the key ideas here are things like, well, you can have a beam splitter that kind of dictates how much light goes in one direction versus the other. And that's the splitter itself. How much light you divide into these two directions depends on the weight of the neural net, and then the intensity of the light coming in is the activation. So that's some of the exciting work that's going on in computing hardware, making it more efficient. We can also make the algorithms themselves more efficient. In particular, there's been a huge amount of work in the design of efficient DNN algorithms. We can roughly categorize this work into three various areas. One is what we call network pruning, which is basically setting some of the weights of the neural network to 0. And we know that anything times 0 is going to be 0, so we can save energy there. We can also come up with more efficient network architectures. So we can have these large networks or filters that we decompose into smaller filters, for example, like depth-wise or point-wise layers. And then there's also been a lot of work looking at reduced precision. Can we reduce the number of bits of the multiply and accumulate, or the max and the weights? In general, a lot of this work, particularly the network pruning and the efficient network architectures, focus on reducing the number of max and weights. But the real question, if we care from the systems point of view, is does this translate to energy savings and reduced latency? And in particular for this talk, does this translate into energy savings? Well, unfortunately, a deeper dive into this shows that actually a number of max and weights are not good proxies for latency and energy. For example, if you look at this plot released by Google, they show that the number of operations does not approximate latency well. So for example, for a given number of max, you can have a 2x swing in terms of latency. And for a given latency, you can have a 3x swing in terms of max. Similarly, just by looking at the number of weights, for example, having a small network alone is not going to be a good metric for energy, because actually you need to account for all data types. So for saying that energy is determined by data movement, it's not just the weights that are moving through the hardware, but also the input feature maps and the output feature maps and so on. And we can see here, from example, looking at GoogleNet, the weights only account for 22% of the energy. So really, if we want to design energy efficient algorithms, we really need to focus on the direct hardware metrics like energy efficiency and latency, as opposed to number of weights and max alone. So one example of doing this is incorporating energy into the network pruning algorithm. So in the past, what folks looked at was they looked at the magnitude of the weights and then removed the weights that were small. And so for the same accuracy, this can give you a 2x reduction in energy consumption, which is great. However, we know that the magnitude of the weight really doesn't have very much to do with the energy consumed by the weight. And actually what you'd like to do is remove the weights that consume the most energy. And so one way of doing this is that we could sort the layers of the neural network in terms of highest energy layers to lowest, and then start pruning the highest energy layer first. And the idea here is that hopefully you'll be removing the highest energy consuming weights first. Because we know as we remove more weights, then the accuracy is also going to drop. So you're trying to get a better trade-off between accuracy and energy. And by doing this, by factoring in energy into the pruning, so energy aware pruning, we can now reduce the energy consumption by 3.7x, which is about 1.7x less energy than using magnitude-based pruning, and this is within the same accuracy. So the key takeaway message is that it's really important to directly target energy in the design of efficient nets, if that is the ultimate goal, which it is here. Similarly, when you start thinking about not just the weights, but thinking about network architecture design, or using neural architecture search to automate the design of the network architecture, it's important to also there take in measurements like latency and energy to drive that optimization itself. So one example of this is this NetAdapt work that we did in collaboration with Google's mobile vision team. And really the goal here is that we want to automatically adapt a DNN model for a given mobile platform to reach a certain latency or energy target. And we use empirical measurements from that given platform of latency and energy to drive and make decisions about the network architecture itself. In this case, the number of channels, for example, for every given layer. And by driving the design with empirical measurements, again, rather than max and weights, but really looking at measurements, we can get actually a 1.7x speed up for a mobile net with similar accuracy. And another really important key thing I want to highlight here is the fact that this particular approach uses very few hyperparameters, which makes the tuning effort less. And that actually reduces the energy consumption for the actual training itself. So not only do we want to reduce the energy consumption of the resulting model, but through the training process, it's also important to reduce the energy consumption as well. And the fewer hyperparameters you have there, then the less tuning that you have to do. Finally, we talked about in-memory computing. It's also important to think about how you might want to design DNNs for this new emerging type of processor. And it actually could be quite different from how we typically design DNNs from our existing digital processors. So for example, if we take a look at the accuracy of DNNs on existing digital processors, they might be different from how they might perform if you run them on these in-memory computing processors, because you have the factor of non-idealities in in-memory computing. So it's important for the network to be robust to these non-idealities. So for instance, shown here, if we look at how these networks might rank with zero noise, the top ranking accuracy or the top accuracy network might actually not be the top one when we start injecting noise. It actually falls quite quickly. And so basically the same networks that perform well on digital processors might not perform well on in-memory computing. So that's one thing to think in. So again, we need to rethink the design. Another thing is, again, there's this trend of reducing the number of weights in DNN, and this might be less desirable for in-memory computing. One, because the main focus of in-memory computing is reducing the weights of the data movement, the data movement of the weights. And so as a result, if reducing the number of weights is not going to help if we've already reduced its data movement. It might be more beneficial to reduce the data movement of the activations. Another thing is, as we mentioned, you need to convert from analog to digital, and there's some overhead for that. So it might be useful typically in these architectures to have, in these in-memory computing processors, to have a very large array. But then if you have very few weights, you might have very poor utilization of that array. So while for in-memory processing or memory computing, it might be preferable to have shallower and larger filters. This is quite different from the current trend of deeper and smaller networks for digital processors. So really, again, when we're designing these efficient DNN algorithms, we need to think of the computing fabric below as well to get better results. And there's a lot of research in this space. So actually, we recently published a book on this topic, really kind of cross-cuts from computing hardware to computing algorithms, and how can we do this efficiently for deep neural networks. So I invite you to visit that if you're interested in this topic. All right, so moving from how to compute to where we actually compute, this also has a lot of implications in terms of the energy consumption itself and the carbon emissions and how it relates to the compute energy that's being consumed by how we compute. So where we compute, one thing is the energy source itself. So depending on where you're doing the computation, the electricity grid in that region might have different levels of carbon intensity, which is basically the ratio of the carbon emissions or the weight of carbon emissions over the amount of energy that's actually being produced in kilowatt hours that we're showing right here. So we should factor that in. Also, if you're using renewable energy, that percentage of renewable energy varies with the time of day. So obviously, for example, during the daytime, you're going to have more solar energy available than in the evenings. And so that's something to consider. These vary. Also energy delivery. So once you've acquired this energy, how do you deliver it actually to the computing hardware and computing energy itself? You need to factor things like power conversion from going from, let's say, AC to DC, the loss in the wiring that you're sending it, changing in voltage, and also cooling costs. As we mentioned, computing hardware generates a lot of heat, so you also have to spend energy to remove the heat or cool it down. A prime example of this is in the data centers itself. So shown here is a breakdown of the energy consumed in a given data center. Typically, they measure this efficiency of converting from energy to compute energy as the power usage effectiveness, or PUE, and it's the ratio of energy over compute energy. And typically, this is in the range between 2 to 1.1, where 1 is optimal. So for example, if you have a ratio of 2, that means only half of the energy that you are generating actually gets used by the computing hardware. And as it turns out, this is an exciting opportunity where machine learning can actually help improve this efficiency by providing better cooling. Okay, so we go from how to compute, where to compute, and now we should look at what to compute itself. And this is really trying to factor in, where do the compute demands come from? They come from number of the requests that we get, the amount of data that we need to process, and the required quality of result, which we typically think of as accuracy. In order to reduce the number of requests, one thing that we can do is make hyperparameter tuning easier. We already hinted towards this. If we can, for example, reduce the number of hyperparameters to tune, we can reduce the amount it takes to do training, for example, to find the right hyperparameter. Reproducibility is also very critical for reducing unnecessary requests due to replication difficulties. So if you can make your results easy to replicate, that's going to be fewer requests that need to be issued, and thus, therefore, less carbon being generated. This is, of course, also good for advancing research in machine learning, and there's a lot of ongoing efforts both in the machine learning community as well as the systems community. We want to reduce the amount of data that's required because we know that data movement is expensive. So thinking about ways that we can exploit data reuse, and thinking about new algorithms that are more data efficient, and that could maybe incorporate prior knowledge into these DNN models. This is already kind of an area of research in machine learning in general, but there's an additional benefit now that it also has energy benefits if you need to use less data. And then finally, we want to evaluate carbon, like the trade-offs between carbon emissions and quality of result, right? So what is the cost benefit of these situations? For example, is it really worthwhile to get that 0.2%, let's say, increase in accuracy for ImageNet for a huge amount of increase in carbon emissions for much longer training time or much less efficient models? These things should actually be taken into account. And in order to really assess this, we also need a deeper consideration of what is a meaningful quality of result for a given task. So for example, again, look, using ImageNet as a example, is achieving 0.2% better accuracy on your ImageNet data set actually going to allow you to achieve a good quality of result in your final goal? So understanding the trade-offs there is really important. Excitingly, there's also a lot of things that we can also do today that kind of, best practices can help us improve our efficiency. So we have a lot of, hardware and out there that can be already very energy efficient. Can we make those energy efficient settings or configurations the default or make them very easy to access? This requires, software and framework support for things like reducing precision and specialized hardware that's easily accessible. This exists today, but it could be made easier. So really reduce the barrier to entry so that this could be the default for many practitioners and researchers to use. Can we measure and report the energy consumption and carbon emissions so that people know what their carbon footprint is? This requires software and hardware support to measure the energy consumption and kind of system level support to report the carbon intensity of whatever given energy source that's being used. There's already research that's emerging in this space. In particular, people are looking at frameworks for standardized reporting. So I invite you to take a look at this archive paper. They also have some nice commentary on how to reduce carbon emissions or think of carbon emissions in this space. With this information, then it's important to try and run your experiments when feasible in locations at times where there's low carbon intensity. And again, ensure reproducibility for the obvious reasons. And what's really exciting about all these things is that much of this we can do today or in the very near future is just a matter of putting in the engineering effort to enable this. So what are the key takeaways? Because we covered a lot. So the first is, in general, at the very high level, we want to jointly consider energy efficiency and accuracy in machine learning research. We want to consider the trade-offs between accuracy and energy for a given application and maybe try and develop data efficient machine learning techniques that also benefit energy efficiency. When we're designing machine learning algorithms for energy efficiency, we should actually make sure that we directly target energy consumption as opposed to just looking at number of max or weights. And also look at designing specialized machine learning hardware that really reduces data movement. In our day-to-day activities, we should incorporate energy efficiency considerations in our best practices. So we should lower the barrier of using existing energy efficient computing options and enable reporting and measuring of energy consumptions and carbon emissions. We should try and compute in the locations with the lowest carbon intensity and highest power efficiency. And again, reduce unnecessary computing by ensuring reproducibility. So all of these slides are available on our website. We've done a lot of work in this kind of efficient computing space. And so I invite you to visit some of the other resources that we have on our website, including videos. And again, if you really want to do a deep dive on efficient computing, primarily for deep neural nets, I invite you to visit this book. Thank you very much.
Thank you for attending my talk. My name is Diana Morculescu. I'm a professor of electrical and computer engineering at the University of Texas at Austin. I'm also an adjunct faculty at Carnegie Mellon University. I will tell you a little bit about when climate meets machine learning and what is the connection between hardware and machine learning and how we can do their co-design. This is joint work with my collaborators and students at Carnegie Mellon. So what is the connection between machine learning and climate? Well, the connection comes through hardware. Machine learning applications have pushed hardware to its limits. We see them everywhere, from automotive to smart home, mobile wearables, VR, AR, and drone applications. But to push these machine learning applications to the edge, we really need to consider hardware constraints. They are the key limiting factor for deep learning to move to mobile platforms. To keep this in mind, consider the object detection that drains the smartphone battery in less than an hour. Think about how energy consuming this is and how we have to work much better to make this more energy efficient. Other constraints have to do with pushing inference to the cloud, and that means increasing the edge to cloud communication, which affects user experience, as well as on-device inference response time. That means that some of these constraints may not be maintained. So when we try to achieve this machine learning model design under hardware constraints, we discover that it is actually really hard. In general, finding the deep learning model with optimal learning performance is hard, but when you put everything together, the deep learning model hyperparameters, number of layers, units, the learning rate, this is a huge search space. And we're trying to find the machine learning model that satisfies a given performance or classification error. When you add to this huge search space, the design space of the hardware, it becomes even more complicated. So to give you an example, assume we consider the energy cost or energy consumption for these machine learning models. As it turns out, you have up to 40x difference for these models, depending on the platform and the type of model that we consider, for the same type of classification error. So the challenge for us is to identify which of these models at the knee right there that have minimum error, but also have minimum energy, are the best for our application. To do so, we will need to follow through 12,000 models, 800 GPUs, or almost 62 GPU years. And that's the equivalent of 68 tons of carbon dioxide, which is more than half of a US car lifetime and 34 times more than an east to west coast flight. Now, we can't really optimize a model that we cannot measure. So that makes the point for developing joint deep learning hardware models. Typically, a deep learning practitioner will need to identify what are the design space components for that machine learning model. But a hardware designer will need to look at the hardware constraints. Together, they will need to achieve deep learning objectives like accuracy, but also hardware constraints like energy, latency, or perhaps battery lifetime or memory. So we hope that our framework will be able to accomplish these challenges. And the first thing we want to achieve is the ability to measure energy, latency, and power consumption. And our framework, dubbed Neural Power, achieves this with a 90% accuracy for hardware metrics, power, energy, and latency for deep learning applications running on hardware platforms. How do we achieve this? Typically, this starts with the machine learners that need to identify a convolutional deep neural network architecture. But then we want to characterize it for a given target hardware software platform. So we develop layer level models and network level models in the Neural Power framework. These determine very brief, detailed power, runtime, and energy cost with breakdowns that tell you which of these layers and which of these networks are costly in terms of latency for inference or power and energy. This provides guidance to the machine learning developers and also to the hardware developers, such that they achieve a best compromise for both performance and hardware. So what are the components of Neural Power? If we think in terms of network level models, the energy is basically the product between the latency and average power, which in turn is summed up across all layers. In this case, PN, TN are the different layers. Runtime or latency is end-to-end computed for each layer and added across throughout the network. And power is the average power for the entire network or the entire machine learning model when it's run on the platform. Each of these are gathered through profiling, and then models are built, as described here, I'm not going to go into a lot of details, but they are typically polynomial terms, polynomial models with additional terms that accomplish or link us to specifics of the computation, like, for example, number of multiply accumulate operations. The feature space for these polynomial models consists of the kernel size, stride size, padding size, so all the features that the feature space that are important in convolutional neural networks. Similarly, for the power model, we have another polynomial term, a bunch of additional terms. So with this, we accomplish the model selection, and we fit these two models for a variety of synthetically generated neural networks. And how good is this? By comparing to an existing framework, Paleo, which was published right before our work from ACML 17, we accomplish a much better root mean square percentage error as well as root mean square error compared to the original work that they show for a variety of convolutional, fully connected and pooling layers. And as you can see, the estimation error drops from almost 80% to around 11%, which is impressive. We also perform the same thing for power consumption, and compared to the actual model size, as well as the original type of convolutional or fully connected network, we're able to achieve less than 10% accuracy error, meaning 90% accuracy. So when we put everything together, we can see the network level results breakdown. And as you can see, for the fully connected layer 6, which is right third from the bottom, for runtime for BGG16, you can see that we're actually able to identify that as the most time-consuming layer, as opposed to prior work, which was unable to identify that. Furthermore, we're able to preserve the ordering in terms of the latency spent per layer compared to the original actual platform numbers. For power, for the same network, VGG16, we achieve very good agreement with the profiling results, and therefore neural power is able to estimate both latency and power appropriately within 90% accuracy. When you put everything together, runtime is estimated for a variety of networks, from VGG16 all the way to AlexNet and others, with accuracy that is very close to the actual runtime and actual power. And if you can compare this with energy, you can see that also energy, which is the product of the latency and average power, these are almost very close with great agreement between the actual and the estimated numbers. Now, how can this be used? When you look at other ways to compare different kinds of networks, not just in terms of accuracy, but also in terms of their energy efficiency, you can look at a combined energy precision ratio metric that tries to minimize both the error as well as the energy per inference. And depending on the factor alpha that we consider here, we can give more weight to the error, classification error, meaning we care more about the machine learning performance, or we can give more weight to the energy, so the hardware metric. So as you can see in this analysis in this table, depending on the alpha values, depending on whether we care more about energy or whether we care more about accuracy, different networks are considered as winners. Most of the time is AlexNet, but when we care more about accuracy, BGG16 is the winner. This kind of methodology is general. It can be applied to any type of platform in addition to the one we presented here. And the code is available. You can use it and apply it to other platforms as well. A second component that is essential in identifying or reducing the cost for finding these neural networks on a particular platform has to do with searching for the right configuration. As I mentioned, this is a very costly process. Typically, neural architecture search can bring about an order of magnitude improvement in energy or latency if we take into consideration the hardware metrics, but it's very expensive. As I mentioned before, it can take quite a bit of time. So our work in single path neural architecture search, which is hardware aware, allows for that to be done 3 orders of magnitude faster. The basic idea is the following. Typically, AutoML is used to identify convolutional networks that provide the highest image classification accuracy, for example, under given latency constraints, for example, so that they can run properly on a smartphone. Typically, they start with a search space, and then they use some sort of optimization formulation to perform the neural architecture search. But to be able to do so in a hardware-aware fashion, you need a latency model like I presented previously. The issue, though, is that finding the proper network configuration can take more than 100 of GPU hours, and as I mentioned before, even GPU years. So the question is, can we reduce the cost for identifying these neural architecture configurations that satisfy these hardware constraints? And the answer is yes. We started from the basic multipath differentiable neural architecture search approach that starts with multiple different types of paths that can be considered and selected during the architecture search process. A supernet considers all these candidates as a separate path layer, and therefore the NAS problem is viewed as a path level selection problem. So in other words, we need to identify which of these paths is selected. Only one can be selected for a given architecture. This is an expensive combinatorial large design process, and it's typically very costly. Our work takes that in a different direction by combining in this supernet in a single superkernel. In other words, instead of looking at all the possible parameters, weights that are part of all of these multiple paths, we train a single, the largest kernel in the superkernel. And the problem of the kernel level selection is an efficient one because the number of parameters per layer is the one for the largest candidate operand only. So that makes it for a more efficient architecture search. We do so by using this differentiable encoding done in a novel fashion. This approach allows us to achieve state-of-the-art accuracy for ImageNet with more than 3 orders of magnitude reduced search cost. So how do we make these architectural decisions differentiable? We start by having the selection variable, looking at whether you choose just the inner kernel or also the outer kernel as well. But this selection variable obviously is not differentiable. So we make it differentiable by using a group lasso approach that allows you to perform trainable kernel threshold using a trainable kernel threshold variable during the search learning process. And you can do this not just for the kernel selection, but also for expansion ratio, which is considered in this case expansion ratio 3, 6, or just drop out of the layer, again with group lasso and trainable channel threshold variables. And when you put everything together, you get the search space that is differentiably searched, and you can basically use any off-the-shelf optimizers like stochastic gradient descent, for example. By doing so, we're actually able to put in this objective not just the cross-entropy loss that quantifies accuracy, but also this mobile runtime loss term that quantifies the hardware, a specific metric in our case, latency for this mobile smartphone platform. In our case, this platform is a Pixel 1 phone. And we have all these latency per layer models, which could be developed or detailed as I described before. And using this type of approach provides, again, using an architectural choices as a selection process for the latency as well, provides good agreement between the predicted and actual measured runtime on the platform. We performed a neural architecture search process and compare with existing work. On the left, you have MobileNet V2, V3. These are manual designs that do not involve architecture search. On the right, you have all the standalone NAS approaches, as well as the multipath NAS approaches that we based our work on. And then single path NAS achieves state-of-the-art accuracy with the same 80 millisecond runtime that we have on Pixel 1, just like all the other approaches. The difference, though, is that it achieves this configuration in much faster time, more than 3 orders of magnitude faster. And at the same time, if you put it in terms of carbon footprint, at a fraction of carbon dioxide in terms of overall impact. Now, if you put it together, there are other things that one could do in addition to searching for the architecture search. You could cut down the model size by using quantization, and we also have work here, flight-NN, as well as pruning. In more detail, typically you would start from a full precision, and then you could go all the way to a binarized neural network. In between, you might have different quantized, lighter versions of the neural network that allow you to perform all these multiple accumulate functions with smaller footprint, memory footprint, as well as using just logic functions as opposed to full precision approaches. You could also improve on their accuracy, like in our work we presented last year, by allowing flexibility in the number of bits for representation, as well as making binarized neural networks even better by using regularized loss to improve accuracy. And finally, you could also add pruning as an additional approach to make these even better in terms of low power and efficiency. So when you put everything together, you can expect, in terms of training, 3 orders of magnitude in efficiency, as well as up to 2 orders of magnitude in inference when you deploy these models. Overall, when you implement this methodology, you can perform optimal design for a hardware-constrained deep learning application running on edge, which can enable you to cut down on the energy cost during both training and inference. With this, I would like to thank you for listening to my talk, and I would like to thank my collaborators at Carnegie Mellon, Google, Microsoft, as well as my students. If you're interested, you can find our code and more information on these slides. Thank you.
All right. Well, thank you everybody for attending, and thanks to the 3 speakers for 3 incredible talks. We're very, very lucky to have such an incredible lineup, and I really, really enjoyed all the presentations. It's rare to see this kind of work presented one after the other in rapid succession, and it was really, really interesting. So please, the attendees can write questions in the chat. We have a lot of eyes on the chat, so every time you ask a question, it will pop up. We will see it, and we'll get the speakers to answer. But to just get things started, I have a few questions. I have a lot of questions. I think this is really exciting work, and it's really timely work. But one thing that came up in the chat, and I've seen one of the attendees ask about it, was about the importance of, if you could focus on one thing right now to try and make energy consumption better, and the two aspects you could focus on are training models and tuning them versus after you train them and tune them, the deployment and the energy consumption at deployment time. Which one do you think it has the biggest impact in terms of energy consumption? So the premise that I have is that which shows up when in this accounting for tuning as part of the total energy consumption, is that the more you query a model, you use it, you run forward and backward passes, the more energy you require. And at some point when you deploy it, you have a lot of users, a growing number of users using a growing number of models that are of growing complexity. And so do you think these 2 lines of cost will intercept each other and one will overtake the other? Do you think one is clearly ahead of the other? Yeah. So maybe I will ask everybody, but I think I will start with Emma, because I think in your talk you mentioned you talk a lot about training, and so I was curious to hear what you think.
Sure. Yeah. Yeah. So I've just been focusing on training because I think there's been less work there, and I think people sort of actually discount the amount of energy that is used for training, actually, because we think in an ideal world, you train the model once and then do inference a bajillion times and it's wonderful. But in reality, in production, you're retraining these models on a very regular basis on more data every time, as you get more data. But But yeah, I mean, there's been a ton of work on making inference more efficient, and I would love to do a follow-up work to, you know, our earlier work on like the carbon footprint of training these large models. Unfortunately, I haven't quite figured out a way of quantifying that for inference. You know, it'd be great to figure out, like, for 5 minutes of browsing your Facebook feed or something, like, what is the carbon footprint of that? Facebook would never let me, like, actually release that, but, like, maybe it's in some form, you know, some way. I think that'd be really interesting, but I think it's hard to quantify. I mean, my intuition, sorry, I'll stop talking really quickly.
No, I have a follow-up. Yeah, sorry, you were saying?
Yeah, I mean, I'd still say my intuition is that, like, if you could compute, like, the amount of energy being spent on inference versus training, probably inference is going to be, like, way more.
Yeah. But your comment about the Facebook feed reminded me that there was a page, I don't know if it's still live, on the carbon footprint of a Google query. It used to be live at some point. I don't know if it's still even updated or. But that's
now that they have Bird in there, they like stopped reporting
it. Yeah, that's interesting, because if you think about it, when you go on a website or whatever, you know, web service, in the background that queries so many models. If you start thinking about, like, when you write an email and it does character by character prediction of the next character or the next word or the current word, that's a lot of queries.
Yeah, I think for making policy decisions and stuff, it's actually going to be really important for us to know, like, what these numbers are. Like, as the world moves towards, like, AI being integrated more and more everywhere, you know, if everyone starts using, like, Siri or Alexa or whoever to, like, turn their lights on and off, like, what is the possible savings of being able to automatically turn the lights on and off versus, like, the cost of, like, having to do this entire, like, NLP pipeline every time you want to, like, flick a switch, essentially.
Yeah.
So I think it's important, but it's hard.
Sounds great. Going clockwise in my own view of teams, which may or may not be the one that you have. I was curious to see what Diana thinks as well.
Sure. So, I mean, we actually had a short chat before we even started live. So I actually think there's quite a bit more understanding about what happens with the cost of inference and serving as opposed to a cost of training. And I think if we push models to the edge, truly to the edge. So right now, queries that Alexa queries or even smartphone queries actually have to go to the cloud anyway. So if you're going to push them to the edge devices, then you need a way to characterize them in terms of power on that device, not in the cloud, especially because other costs may be hidden or hard to characterize, the cost of communication. And actually, there are additional issues related to that, privacy. I'm not going to go into details on that, but I actually think once you have an idea of your platform, it's actually pretty, like in neural power, we were able to characterize relatively easily the power, energy, latency of these constructs that we see in neural networks. So once you develop them once for a given platform, you can use them in composable fashion. The question becomes more complicated if you also want to do co-design. So if you want to build an accelerator, then you don't know what the hardware is. So in that case, you need a good starting point, and then you need to iterate between both the model, the machine learning model, as well as the hardware together. But I actually think there is a lot of expertise in power modeling, energy modeling, latency that can be translated to carbon footprint. Right now, we used really high-level back-of-the-envelope calculations to find the carbon footprint, but there's no reason why we can't be more precise. And I think that's very important. Yeah.
Thank you. So I have from the chat, since I have you on the line, essentially, we are all on the line, but you were talking. There is one question for you specifically, and the question was: has neural power been extended to include extrinsic sources of latency, such as network interconnect between multiprocessors spread out in space?
Right.
Also, any instrumentation regarding total memory footprint?
Right. So right now, neural power is targeted for a given platform. So you have the methodology, you train the power, energy, and latency model for that platform. So you do model selection for a given platform. Everything like the sources of latency, network interconnect, memory footprint are embedded in the models that we build. If you want to be hardware aware, such that you can actually do this hardware design at the same time, then the model cannot be just neural network specific. It has to be hardware specific. So you're going to have to do model selection and model training for power, energy, and latency that includes the configurations for the hardware, including network and memory footprint. So in some sense, it is included, but it's not, visible. It's hidden. You can expose it such that you can use it as a knob. So that's always possible. The challenge, as I said in my comment, is that the model becomes more complex. So you need a way to separate the two. So it is possible because it has been done in the past, especially in embedded system design. There's the concept of hardware software co-design, and people have done this successfully. So I think it can be done in this case too.
That's good. Thank you. So now moving on to Vivienne with the same question, with the first question that I was asking, which was the attention paid to training versus inference. Do you think inference will overtake training? Is already ahead of training in terms of total impact?
So I think I guess I'll answer the question in a different way. So I think certainly for each of these things, we know that inference consumes less energy than training, but then there's more inference requests. I would say, similar to what Diana said, that has been a lot of work in making inference more efficient. So if you're talking about which one has the most excess compute, which has more possibility of improving, I would actually say the training side has a lot more possibility of improving. Inference, I say, is that there's been a lot of work that might be more challenging on that extent. On the inference side, though, you do have, and this actually came with a discussion from Emma on the chat before, what I was thinking about for inference is you can actually tailor it to make it much more application specific. And this kind of also leads to what Diana was saying about like specialized hardware. So you have this, often a lot of inefficiency, and including to data movement, comes from flexibility of the design. And if you can tailor it to a much more specific demand or specific application, then you can also shave off a lot of that inefficiency. That's both in the algorithm side and in the hardware side. So we did a study of this in this ISCAS paper, I think it's 2017. We're just comparing like basically handcrafted approaches, but more like hardwired weights versus general weights that can be reprogrammed. And there's still like orders of magnitude difference in terms of efficiency. Another good example of this is if you compare running DNNs on images compared to video compression. So prior to all of this, I was working on video compression, and the energy that we spend on video compression, which it's very ubiquitous, is again orders of magnitude less energy per pixel than DNNs. And one aspect of that is because we very much specialize video compression. It's standardized, so you could just imagine like the weights are fixed basically, and if you can fix them for this application, the efficiency is much better. So I think from that point of view, there's a lot of opportunities on the inference side of things as well. But just in terms of just inefficiencies, in terms of, even like I tried to really emphasize on my talk, and I think Emma also mentioned like reproducibility, just like people doing the same thing over and over and over again. There's a lot of waste just there happening that's really unnecessary.
That's great. That's interesting. Thank you. Which kind of leads me to a second question that I have. Meanwhile, I'm trying to interleave questions that. Actually, we have a question for the panel. What would our AI world look like when transformers go from tera parameters to peta parameters, and if there isn't enough computing or energy available to train them to reach further advancements? This is an open mic, so whoever wants to take this one.
I'll go ahead and I'll initially say, I think this is like a fun direction, for a couple companies to do, in the next couple of years to see how far we can push these models by just making them bigger. But I think they're not going to be useful unless we can make them smaller. And I think at all these companies also, there's a bunch of engineers frantically, and researchers, but mostly engineers frantically trying to cram these models into production with quantization and distillation and maybe sparsity sometimes. So, I think they're just not going to be in production unless we can actually make them a lot smaller. And I think also in production, people are typically not running on the hardware that has enabled this, TPUs and GPUs. Actually, it's still CPUs at most companies. And no researchers are really interested. feedback that I've gotten is like it's not interesting from a research perspective to do stuff on CPUs because everything is just going to be GPUs or like specialized, co-design hardware in the future. I don't know. I'll just end my rant there. Yeah.
No, we love ranting panels. That's what makes panels interesting. Diana, Vivian, anything to add to this? Otherwise, we can.
So I cut out a little bit for me, but like Emma, your comment was that researchers don't want to use specialized hardware for their research. Is that?
Oh no. Actually, just like CPU. So like I think currently a lot of companies are still using CPUs in production to run their workloads.
Yeah, so I think people need to make these types of platforms, efficient platforms, more accessible. I think that's really one of the key things, right? I think there's a lot of research, but like actually making it useful and having, I think the software stack, people are working on that, but to make it much easier to use. And I mean, like it is kind of ridiculous that this stuff exists, but someone just needs to close the gap to make it usable and also educate people on how to use it. Also, I mean, I've heard this anecdotally that people, in the past didn't want to use 16-bit floating point because you're going to lose a couple of like point whatever percent loss in accuracy, but the efficiency is much higher, right? So also as a community, I think it's important to properly evaluate the trade-offs of doing compute more efficiently versus the incremental gains in accuracy or whatever quality.
Yeah, before we move on, I wanted to see if Diana had anything to add.
Sure. Yeah, so I mean, the question was whether we're going to have enough computing energy or dollars. I don't think that, I mean, we are here because GPUs have democratized like Vivian said, have democratized access to the kinds of applications and advancements that we see. The reason we now talk about deep learning is because of the computing, because of the advances in the hardware. So, I mean, machine learning neural networks have been around for more than 40 years. And now everyone is doing research on them because they do have access and they think they understand. I don't think we do understand what happens in all neural networks or all kinds of machine learning models. But we do have access to these resources so far. And I actually don't think, I think democratizing access is something that we need. I find more and more it's more difficult, especially for academics, unless they have access or a partnership with industry to actually move forward in advancing these things. I mean, Emma's models, they take a lot of resources, right? My students, whatever research they do, pretty much they have to have internships for at least a summer every year, if not more than a summer, to get data and to get meaningful results. So I think what is needed is a meaningful partnership between academia and industry to actually make sure that we have energy or dollars to continue advancement, because we have uncovered the more computing we have available, the more we can understand about machine learning in general. But machine learning is now here, computing is here, at least in access. So we need to bring it here to advance to the next level. So it has to be a partnership. So it's a question of how we can do it, not a question of if.
Yeah, I agree, and I've seen this play out in my own research with collaborators who are in universities, and used to be at Microsoft, and they and at some point I had to continue projects, and computational resources became a problem because we have them on this side, they have grants and everything, right? But it's the scale is different. So I completely see your point. I thought I saw a proposal recently about like a national supercomputer for AI workloads specifically. I don't remember. It's one of those things that floated in my Twitter feed. I didn't really go very deep in it, but yeah, it's definitely a big issue, I think. And it's an issue as we have interns who are now about to finish internships, right? And access to compute is becoming a problem.
Right.
But something that came up in this discussion, and it's super timely and top of mind for a bunch of people because it's the NeurIPS reviewing deadline tomorrow. So please, if you haven't submitted your reviews and you're watching, please submit your reviews. But now the new thing in the NeurIPS format was that you have a statement of impact. And I look at a lot of paper in the neural architecture research and Bayesian optimization and that kind of style community, and pretty much, I would say 20 statement of impacts were on the reduction of energy consumption. And some of them I think were genuine, and some of them were just because I reduced this thing by an hour. So this used to take 24 hours, now takes 23 hours. So statement of impact, I reduced the carbon footprint of this model. So my question is, I will get to my question. My question is, there seems to be a part of the community of, here well represented by you, which truly seems to care about energy efficiency and energy consumption of models and sustainability of progress in AI. There seems to be another part of the community that doesn't seem to care at all. Like they look for those, 0.2%, not a typo, 0.2% improvements at the expense of, I don't know, as a proxy for energy, 200 million more parameters. And then there seems to be a middle ground in the community, which seems to be caring a lot about, well, let's make this faster. And by making it faster, I can make the point that it's also more efficient. So my bigger question is, how do we actually get everybody, all these ends of the spectrum together, such that energy consumption of a model becomes like a primary metric in a table in a NeurIPS paper? Because right now accuracy is in bold, and then you see number of multiply adds, or multiply accumulates, and then you see maybe number of parameters. But is it a matter of getting more accurate measurements, more easily accessible measurements? Whoever wants to take it.
If I can take that, I think this happened in other fields, right? I mean, if you think about power consumption, it has to do with electrons and holes and things moving. And the fact that Vivian and I come from different fields, actually, I'm not a machine learning expert. She's a circuit designer. At least she started as a circuit designer. I studied as a computer hardware CAD many years ago. But this happened in computer architecture 20 years ago. So people didn't care about anything but performance. So they threw more resources until they realized what I'm getting is marginal performance. When I say performance, I mean not machine learning performance, but instructions per cycle, or what you have. So so around 2005, and I think we've seen one of those charts there, everything started to flatten because if you don't address power, things start to come bite you from behind. So that's where we moved to multi-core, and that's created the GPU revolution, and this is why we're here now. So I think something similar happens here. What I think needs to happen is a few things. First of all, there needs to be an acknowledgement from the community that this is important. So we can come up with models, we can come up with accurate ways to characterize and come up with efficient ways to identify the best way to design the hardware needed for machine learning. But if there's not an acknowledgement that these are important, and like you said, deserve a column that people care about, people are still going to hone in. I went from 75.62 to 75.82. That's still going to be important. Of course, once there is that acknowledgement, we need it. Then we need accurate models. We need a way to connect the physics to the machine learning model, including the hardware in between. And once you have the models, then you can say, okay, how do I do a better job of building my machine learning models and the hardware, or together, either separately or together, to deliver on the promise? So I know it was a long-winded answer, but I think it needs buy-in from the community in general. And, the answer to the broader impact of whatever work is submitted to NeurIPS should be quantified. I mean, it's okay now because maybe we don't have the tools to quantify them properly, but once these tools exist, they should be usable by everyone. You run your model through this, if it's understood that it's acceptable, and then report those numbers, and then your statement is going to impact energy by this much will actually be backed up by numbers. So I think that's how we get there. I don't know how long it's going to take, but without that, we're not going to bridge the gap, right, between what hardware is able to do now and what machine learning wants.
Thank you. Yeah, no, I completely agree with that. I'm curious to see if Emma or Vivian want to chime in.
Yeah, so kind of building on that, I think another way to build consensus is to identify common issues that we could address that would benefit both improvement in accuracy and advancement of the machine learning field, and improve carbon emissions, which would also be, again, I have to harp on this, which would be reproducibility and understanding the deep learning models. I think everyone should be interested in reproducibility and understanding how the deep learning models work. If you understand a bit better, then you won't be doing like random hyperparameter tuning to get higher accuracy. You would actually also understand if this 0.2% accuracy is actually important. I think maybe as a machine learning field, one should ask, should one care about 0.2%? I mean, we're picking on that number, but like, you know what I mean? Like that, does that merit a publication if it doesn't explain how that was achieved and if it was not achieved through some reproducible means, right? So I think maybe a deeper inspection in terms of where the improvements are coming for, and that should be valued more in the field as opposed to purely what is state of the art, right? In some sense. Yeah. I think that's beneficial for both from a compute side and a machine learning field advancement side. And I think that's something that I would think people should be able to agree on. Now, I think one challenge of that is that to do more like robustness studies, you do need a lot more compute. So there is a little
exactly. If you want to do an hypothesis test.
Yeah. So when you have these models that are super, expensive to train once, doing it multiple times is going to be. But I mean, even when people are doing hyperparameter tuning and they could just release their intermediate results and what did they tune to get there, right? Like, I mean, just being more informative about what you did with the attitude or the goal of advancing the field as opposed to getting a NeurIPS publication. I think that maybe I should put it that way. People should be thinking about contributing from a scientific and understanding point of view as opposed to being able to claim they have the highest accuracy or they have this many publications. And I think that is a joint goal that would at least cut some of the issues. Then I also agree with what Diana said, which is then people should also ideally report the latency on what platform, and maybe from that you can extrapolate how much carbon emissions you have. And I think people have started to work towards more standardized tools to do that. And I think that would be great. It could also be informed by cloud providers also providing some feedback in terms of where, they will know what the carbon intensity is. The person who runs it does. And people who build the frameworks should kind of also have some of those aspects easy to be accessible for the researcher. So I think there's making things more accessible and then working on joint problems, I think, that are important to both improving the field and computing is a good idea to do.
I agree.
So
yeah, go ahead.
Yeah, so I was just going to say, I completely agree with all the points that have been made. Just to go a little bit further on one of the things that Vivian brought up, I think this is also sort of a symptom of a problem that we have in the field. So it's like, why is the metric how can I just get a NeurIPS paper? And it's this pressure that students and junior faculty feel to just publish as quickly as possible. You're coming into grad school, you're expected to now have multiple papers in top tier venues, and I think that encourages this really short-term thinking, low-hanging fruit type of research that's just okay, well, if I get the number higher, the paper will get accepted, which also is a symptom of sort of lazy reviewing, and which is also a symptom of the fact that there's so many papers, it's hard to review. When you get 11 papers to review for a conference, you can't blame people for kind of taking the easy way out and reviewing, being okay, this is an easy paper, they made the metric higher, great, I understand, I'll accept it. So it's kind of really a big problem, I think, in the community is how can we better prioritize doing longer term, more visionary research, and how can we better sort of evaluate people on that, which is harder obviously than counting beans, counting number of papers and things number of citations and things like this.
Yeah, I think that's a great point. I wonder though if one could do an interventional experiment in our brain and remove NeurIPS and ICML and UAI and AStats from existence. They don't exist anymore. Archive is the only venue. Would that solve the problem of accuracy column chasing or table chasing, and would people be more honest about the impact of their experiments and the actual improvement over whatever the baselines?
I mean, I don't think just getting rid of the conferences would necessarily help it. It's still, I mean, I know I've done work that's like making the number higher, right? It's like very satisfying and straightforward. Like in a, research is really hard, but like, if you have this like really clear metric, it's a lot easier to.
Yeah, I was not arguing to remove NeurIPS. I was arguing that how much of this is the reviewing process, which and the conference format and the fact that we have, I don't know, 6 deadlines per year that we kind of have to hit, versus, okay, let's remove deadlines, let's go to a kind of a journal style publishing model where timing doesn't matter really, and you can publish when you're ready, and nobody really reviews it other than the community, by citing it. Would that solve the problem? And to me, it's not clear, because people would still chase the same kind of metrics. But
right. So I mean, oh, go ahead.
You just a short comment. I think you would need to convince, I guess, university administrators that metrics like conference publications and journals.
No. But I'm not arguing for it. Yeah, it was just like a thought experiment. I think conference should say anyway.
Okay. So, Vivian, go ahead.
There's some activities going on the side for a lot of these conferences about reproducibility. So as I understand, there's a reproducibility challenge that happens for NeurIPS and iClear, and so people kind of, when they go through that, and if their paper somehow gets a check, then people know that these things are reproducible. I know on the ACM side, from the systems point of view, there's been these artifact evaluation committees at conferences. So for machine learning, like MLSys, which is a conference for machine learning and systems, we actually have an artifacts subcommittee where like people, after paper gets accepted, there's a whole committee that will verify the code and see whether or not they can reproduce it, and then the paper actually gets a badge. And I think that actually, this could be a motivation, because there's so many papers in machine learning that it would be great if you only looked at the papers that have these badges, because you know that if you pick it up, it actually works, right? And that would actually be an incentive to like elevate it above the rest of the stuff. So maybe that's a way to further push that kind of effort. And that's, again, good for the field and good for computing. More types of these, recognizing papers that have been reproduced before.
Yeah. I actually agree. I mean, my students have been involved in some of these efforts in the systems area, and it opened their eyes into the importance of reproducibility. So when they cannot reproduce results from someone else, there's a lot of back and forth with the original authors, and until they can reproduce, they will not stop, right? So sometimes it doesn't happen, but it's really important to be able to achieve that.
Oh, one follow-up quick thing. So I think academia can provide the manpower for that, but it would be, or person power for that. But I think the important thing would be for companies to provide the compute power for that, because I think the compute effort to do reproducibility is very high, and it would be great if corporations kind of stepped in and helped support that effort. Just in general.
I completely agree.
Microsoft. Sorry.
Sorry?
Oh, I said, hey, Microsoft.
I know, exactly. Well, other companies may be watching. This thing is public eventually. So let's all join forces.
It's good if companies are like, they support reproducibility, right? It's a good thing to be associated with your company.
Of course. No, I completely agree. But one comment that I had as a follow-up is, do you remember at some point NeurIPS had this kind of correct paper format checker? You would upload your paper, you would get kind of like a pass or a fail. Without that, you couldn't really upload the submission. I don't think they did it. I don't remember it in the last couple of years. The server was going down. I mean, it was, you can imagine as NeurIPS scaled, it became unfeasible. But I wonder if there is an equivalent service that could, you submit a PyTorch model and gives you back the energy consumption, at least of the model. Based on just the format, the shapes, that's all you can do. You cannot really pass data. And maybe that could be the stamp, a stamp.
I mean, we did something similar like that preliminary in our group, where we, like, at least from a more custom hardware based on the shape of each layer of the neural net, we could try and estimate what is the potential data reuse, and based on the sparsity, the amount of compute at different levels of memory hierarchy. And that's what we actually fed into the energy aware pruning stuff that we did. But I think that there's a much bigger effort. I think Diana's team has also done a lot of great in like the kind of power estimation based on the incoming layers. I think if there were standardized ways of doing this, actually, you know, who would be great at doing this? Companies who build GPUs and those hardwares. If they also released a model like that, that would be again making their platform much more attractive to users. So there's an incentive to do that, maybe. So
yeah, I think that's a great point. Any last comments before we close? All right. Well, thank you again. It has been an honor to host you. Thanks so much for the attendees. There is going to be closing remarks starting in a second, so please stay around for those. And thank you to the speakers again. This was incredible.
Thank you so much for having me.
Yeah, this is
Thank
great
you.
as well.
Well, hello again. I'm Sandy Blythe, and I wanted to take a moment to thank you for joining us. We're grateful to all of you who've been able to come together virtually to participate and engage in discussing the current and future perspectives on the frontiers in machine learning. I know the MSR team got a lot of value from the rich content and the interactions, and I hope all of you got a lot out of it as well. Now I'd like to invite Vani Mandava, who is our general chair for the event, to provide some of her perspectives.
Thank you, Sandy, and thank you all of you for tuning in to the concluding session of this event. The Frontiers in Machine Learning event was built on the tradition of the Faculty Summit event that Microsoft Research hosts in Redmond and has been doing so for the past 2 decades. We had to cancel the event this year due to the COVID-19 lockdown, and it took the talent and dedication of many people to pivot the event to this virtual format. Specifically, Chris Bishop, our executive sponsor, and the scientific program committee, our logistics lead, Sarah Smith, and our speaker manager, Jen Vancic, did a heroic effort in keeping everything on track. Greg Tushaw, our producer, along with Henry Honig, Graham Reeb, and many others on Jeremy Crawford's amazing media team in Microsoft Research. There is a silver lining in all of this. We were able to register almost 2,000 attendees for this event from over 300 organizations in 35 countries. We were also able to include a significant number of graduate students at the event this year. This would not have been possible if we wouldn't have transformed this event into a virtual format. All the talks that were presented throughout this event are available for on-demand viewing on the Microsoft Research website. A big thank you to all the Microsoft Research session leads and all the faculty speakers who worked with us patiently and gradually as we transformed this event to what you experienced over the past few days.
So this concludes our Frontiers in Machine Learning event. And while we regret that we weren't able to meet you all in person this year, we're also thankful for the opportunity that the broad machine learning research community has provided us in coming together for the event. Microsoft Research is committed to continuing to foster research and academic collaboration. And during my opening, I mentioned that there were some ways that we support the academic research. I would note that just this last week, we opened the nominations for the Microsoft Research Ada Lovelace Fellowship, as well as our North American PhD Fellowship. Nominations by the Department Chair's office are due for each of those by August 14th. There's always a lot going on at MSR, however, so please do stay in touch with us through all of the ways that you see here on the slide. And also, please let us hear your feedback via a survey. Thank you all, and be well.